going to study systems of equations in this module. So I just want to give you a brief introduction to systems of equations in this video demonstration. A system of equations is more than one equation or more than one function. What we're going to be studying are linear equations or linear functions. Systems can get very complex, involving multiple variables like equations that can involve x, y, z, and even more variables than that, covering several dimensions. For our purposes, we're only going to work with linear, so in 2 dimensions. This is an example of a system of equations. Sometimes a system will be denoted with a brace, something like that, to show you that they are intending for this to work as a system. So you can see there are 2 equations here. These equations are both linear. The reason you know they're linear is because the y and the x are both to the first degree. If they weren't to the first degree or first power, then they'd have a 2 or a 3, denoting that they were to a second or third degree or higher. But these are both to the first degree in both equations. That's why you know they're both linear. So this is a system of linear equations. I'm going to switch to a program called Desmos Calculator to demonstrate how systems work together more specifically. In order to understand systems, I think we need to back up and review what a line is real quick and how a line works. So just let's look at this line, y equals negative 2x plus 4. And just review what we know about a line. The 4 is the y, and this is in y equals mx plus b slope-intercept form. So we know that the 4 represents the y-intercept, where it crosses the y-axis. If you go over here to the line that's already graphed for us, you see the y-intercept is at 0, 4. And the negative 2 represents the slope. So the slope should be, and the slope should always be written in or converted to fractional form. So this would be negative 2 over 1. And what that means is from here, every next point can be found by going down to 1, 2, and to the right 1. And we see the next point, if we hover over it, if we could get to it precisely, it's kind of hard to get to it precisely, is right there at 1, 2, the ordered pair 1, 2. So that's a line. The x and the y in any line are variables. They're not really unknowns. They're variable, which means at any point on this line, we know what x and y are, because I can click and follow this down, and everywhere along the line, x and y is known. It gives me an x and y value, but they change, they vary according to the line. Now here's where a system comes into play. When we look at a system of equations, we're looking at more than one line. So let me enter a different line, y equals 2x minus 4. So I've changed the slope of the line so that they're not parallel. If they're not parallel, they're going to intersect at some point. If they were parallel, that's a phenomenon where 2 lines would never intersect. But I want to see where these lines intersect each other, because that's the point of significance in a system of equations. Now we have a system of linear equations here. 2 lines that intersect at a point in the plane. So the second line is this green line. And again, x and y varies, but I can find x and y at any point along the line. They are known. Now, a system of equations usually has some sort of relationship, and they tell a story together. And I'll show you a real-life example that demonstrates this in just a second. But the most significant part of that relationship is usually the point where they intersect. And when we solve a system, when we use that term, and we're going to solve a lot of systems, when we find the solution, what we're finding is this point of intersection, the point where the 2 lines cross. Line 1 and line 2, the blue line and the green line, cross at the point 2, 0. So the solution to this system is the point 2, 0, the ordered pair, x equals 2, y equals 0. That point will have some significance always. To give you the story of a little bit of the why behind systems of equations and why it's important to learn them, it actually may become more applicable to more of you than realize it at this point in your lives. But I'm just going to show you a really simple, somewhat unlikely scenario, but just say the scenario is this. You decided that you want to start to bake cakes for extra money. And you've determined that it costs you about $2 to make a cake. So this T would represent total money that you're going to spend in this business, because you gotta pay for it before you sell it to make money. So you've figured out somehow that it's going to cost you about $2 to take a cake, but your mom says, wait a minute, to make a cake, but your mom says, wait a minute, there's some expenses for me. You're going to use my kitchen, there's electricity, there's a wear and tear on my stove. So your mom's decided she's going to charge you about $80, we'll say per month. So this is looking at a scenario over a month. What's it going to cost us every month as we make these cakes? And it's going to cost us $2 for every cake we make, plus $80 off the top mom's charging us for her kitchen. If we become really successful and start baking more cakes, she's probably going to increase that cost, because it's going to increase the cost to her, allowing you to use it. So this is kind of like our rent. And in any business, you have these kinds of costs, whether it be building rental, you're going to have insurances you have to pay. This can get very complex, so we're keeping this scenario simple. So that's one linear system. So very simple, $2 per cake plus $80. And if you look at our line so far, and we hover over here, we're at 0.80, which is where we start. So whether we make one cake, we got to pay our mom $80. So we're already out $80 beginning of the month to start. So we're down 80. Now we're going to sell these cakes ideally. So let's set up another function, another linear equation to show how much we're going to make. And we decide that a good cake you could probably get $10 for, maybe more if you decorate it up. But let's just use a nice easy number here. $10. We're going to charge $10 for each cake. So this line, the new blue line, represents how much we're going to make. So each cake we sell, we get $10. And you see that reflected here. When we have 0 cakes, we have 0 money. When we sell 1 cake, we should be at about $10 as we go up. Now we see where this system intersects, and let's look at exactly what that means. So it intersects at the point 10, 100, which means we've now made the first variable, the x coordinate, which now has become our c coordinate, is the number of cakes we've made, which is 10. So we've made 10 cakes. It's easy to see that at 10 cakes we've made $100, because 10 times 10 is 100. But it's the same value for the cost function here, the cost line, where we've made 10 cakes. Now we've paid out $100. And this significance of this is it's our break-even point. So what we've learned is that we have to make 10 cakes to pay our bills, to break even. Now, once we get past that, once we've made the 11th cake, the 12th cake, now we are making money. We're making a profit. And we can determine how much as we go on up. But you can see that's a significant point in this system, because it shows us where we have to land to break even. And a lot of times a business within this cost function will put all their employee costs, they'll put even the cost for paying themselves. So the break even point shows where they've paid all their employees, they've maybe paid their own personal salary, and the business is flush. Now every business wants to make a profit, so ideally you want to get beyond that point. But that's just an example of why and how a system works, and some of the points of significance within